Welcome to Trig subs. So we're going to start this section with my favorite phrase. There's really nothing new in this section. However, you're going to have to remember U subs. You're going to have to remember trig integrals. You're going to have to remember trig identities. You're going to have to remember a lot of stuff. Okay. We're putting a ton of things together in this section. Okay. And finally conquering some age-old nemesis. Remember, if we had something like this, we can't integrate this exactly. Or like we can't integrate this. Or we couldn't. We can now. In the past, we'd have to say, well, this is a semicircle. So for a definite integral, we could evaluate this partial area of a semicircle. For an indefinite integral, though, there's nothing that we could do. Now we'll be able to, along with plenty of other juicy, interesting things. This is some of the stuff that we're going to be looking at today. So lots of square roots, lots of fractions. You might say, Jason, there's no trig here. Just you wait. We are going to be putting the trig in trig subs. All right. So it's going to be fine. It's going to be fun. We're going to be doing some conic sections today. Parabola, we found integrals of parabolas before. That's easy. But integrals of circles, we're going to find, antiderivatives of basically semicircles. Antiderivatives of semi-ellipses. Is that a word? I don't know. Antiderivatives of hyperbolas, stuff like that. Okay, so that's some of the fun stuff that we're doing. And if you remember completing this square, that's going to come back in this section as well. Again, a lot of times you don't get the visualization for completing the square. The idea is x plus 4 squared is x plus 4 times x plus 4. It's the area of this big square. And that's just, well, these three squares. And the question is, well, what's that last square? When we complete the square, we add that last square and then subtract it later, right? Well, this last square has to just be 4 by 4. There's a cool visualization of this. We'll do a little bit of review in the selected homework problems video for completing the square. So that's some of the stuff you've got to look forward to. We're going to start this video by actually, hold on, let me modify this problem and then we'll save ourselves a little work. We're going to start by finding the antiderivative of a semicircle of radius 1, I think. Yeah, that's in my notes. Great. Let's see. That's what we're doing. Let's start with that. We already started. Let's continue with that. All right. So we've done U subs. And this is really just a different kind of substitution. A substitution's a substitution, whether we call it a U sub or a trig sub. But let's reframe our perspective. A lot of the times we'd let U be equal to something. But now we're going to let something be equal to something else. Here's what I mean. Instead of letting U be something, let's let X be something. What happens if I let X be the sine of theta? What are we going to get? Where did this come from? I'll tell you later. But right now, take it on faith. Let X equal the sine of theta. Well, then how can we reframe this integral? Well, that means we get the integral of 1 minus sine of theta squared dx. Oh, we need dx. Well, dx is going to be cosine of theta d theta. It's just the derivative, right? Dx d theta is cosine. So dx is just cosine of theta d theta. Okay, that's no problem. So we got some trig. Well, Jason, this doesn't look that much easier. Well, let's simplify. Look what's going to happen when we simplify. What is 1 minus sine squared of any angle? Oh, remember our trig identities. That's cosine squared of that angle. That's neat. So this really just becomes the square root of cosine squared of that angle times cosine of that angle. This is kind of nice, right? Okay, it's actually not that nice because look at this. This is not as nice as you want it to be, right? The square root of something squared is not always just equal to x. Right? If x is negative, for example, this is not true. This equality is not true if x is negative. Negative 2 squared is positive 4. Square root of 4 is 2. Negative 2 and 2 aren't the same thing. So the square root of something squared is the absolute value of that. So, all right, it's not as nice as it could be. We get the absolute value of cosine of theta times cosine of theta. And this, you can't combine these. Actually, there are some sort of... No, I don't think there's any way that we can combine these, actually. But remember, in pre-calc, we talked about domain and range. Why do we talk about that? Because it matters, okay? I promise that when I teach pre-calc, I don't talk about domain and range because I find it interesting. Sorry, don't tell my pre-calc students. It's because it's going to save us some problems. So let's look. Let's look at where we started. I'm running out of colors here. Let's look at our original integrand. What do we know about x? For this to make sense, what do we know about x? Either think of this geometrically or think of this and like with functions. So geometrically, right? This is a semicircle of radius 1. That tells us something about x. Or if we don't want to take the square root of a negative, what do we know about x? Either way, x has to be between negative 1 and 1. And that's why this substitution works. Because the range of sine is negative 1 to 1. Right? What do we know about sine? We know sine goes up to negative 1 and down, or up to 1 and down to negative 1, and it just repeats forever. So x is between negative 1 and 1, which is good. So what do we know about theta then? Well, normally theta can be anything, but for the sub, we just need theta to cover all of the region from negative 1 to 1. We just need the range of theta, sorry, the range of sine. What's theta have to be so that the range of sine is from negative 1 to 1? And we can just cover it in this interval. This is the same as arc sine, basically. All right, so then theta is theta can be between negative pi over 2 and pi over 2. And we can still get all the x's that we need if theta is in this interval. If theta is in the interval negative pi over 2 to pi over 2, and I know this is lots of pre-calc, lots of pre-calc, domains and ranges and trig, but there's a point, right? X is between negative 1 and 1. So if theta is in this region, then we've got everything covered. If theta is in that region, we're getting all the negative 1s to 1s, and we're not duplicating anything. That's great. Well, what do we know about cosine on that interval? Well, cosine on that interval, this is negative pi over 2. This is pi over 2. On that interval, cosine is at least 0. So all of this stuff in yellow tells us that cosine of theta will never be negative. So if cosine's never negative, this is always equal. Absolute value of cosine is just equal to cosine, which is really nice. Cool. Good. So we need the absolute value until we don't. But you need to know that it's there, and you need to know that it's going away and why it's going away. Because for sine substitutions, this will always be the case. For some stuff in this section, we'll cross that bridge when we come to it. All right. So we're now up to the integral of cosine squared of theta, which we can't evaluate that with chapter 1. Can't use the power rule because there's a cosine. We can't do a u substitution. There's no derivative of anything that we need. Oh, we have to use 3.2 trig integrals. We used the power reduction, whatever I called it, the reduction formula, right? We know that cosine of any angle squared is 1 plus cosine double that angle over 2. And a lot of times we wrote that as 1/2 plus 1/2. Oh, it's all tying together. Pre-calc 1, pre-calc 2, calc 1, calc 2. Actually, I don't know if we use that much. Yeah, we used calc 1. Use calc 1 right there. It's all tying together. So this is the antiderivative of 1/2 plus 1/2 cosine of 2 theta d theta, which we can now take the antiderivative, no problem. 1/2 plus 1/4 antiderivative of cosine is sine. Because of the chain rule, this 1/2 turns into a 1/4. We check our answer real quick. Let's look at this. If we take the derivative of this, do we get back to this integrand? Yeah, we do. Great. I got some bad news for you, though. We're not done. Not only are we not done, but in a U sub problem, this last step is pretty easy. For a trig sub problem, this last step is not always quite as easy. Because look at what we have. X is sine theta. We know X is sine theta. Okay, so theta is the inverse sine of X. And we can say that because we have our domain, this stuff in yellow. This is the domain of arcsine. Okay, so that's good. So theta is inverse sine, arcsine, however you want to write it, of X. Okay, great. So this is 1/2 arcsine. You can write it arcsine like this if you want. Oh, well, what's sine of 2 theta? You can't just do this. So we've got a couple options. One of them is the double angle formula. That's what I would recommend. So we know that sine of 2 times any angle is 2 times sine of that angle, cosine of that angle. You need those trig identities. Don't worry, you don't have to have them memorized. So we're going to get 1/4 and then use this identity. 2 sine of theta, cosine of theta. Okay, we're getting closer. We want everything in terms of X. So you have 1/2 arcsine or inverse sine. They're the same thing. Plus 1/2 sine of theta is X times cosine of theta. Well, what's cosine of theta? We don't know. It's the problem that keeps on giving. And this is the easiest problem of the section. It's okay, though. It's okay. We'll work on it together. We'll do things together, everyone. This problem will be easy by the time you're done with this section. Don't get overwhelmed. We just do baby steps. Well, this is a bigger step. We'll do big step and then some baby steps. It's fine. It's fine. We need cosine of theta. All right, well, let's do that on the next page. We know that sine of theta is equal to X. So the question is, what is cosine of theta? Let's draw a picture. We know it doesn't matter. Since cosine is positive in the first and fourth quadrant, it doesn't matter how we draw a picture. It'll give the same answer. But if this is theta, what does our triangle look like? Well, we can write this as x over 1. Sine is opposite over hypotenuse. So what's the cosine? Oh. We have to use Pythagorean theorem. Right? If this is some a squared plus x squared equals 1 squared. A squared is 1 minus x squared. A is normally plus or minus. Why do we not need the minus? We don't need the minus because we know cosine's positive here. We talked about why cosine's positive here earlier. You could see it again in this situation. Theta is between positive pi over 2 and negative pi over 2. So even if theta is negative pi over 2, even if theta is negative, right, the cosine in the fourth quadrant will still be positive. So we don't actually need this triangle because we know cosine's positive. So cosine will be adjacent over hypotenuse, and the hypotenuse is 1. Oh, great. Cosine of theta is the square root of 1 minus x squared. Great. We did it. So that's going to bring us to a very important point in the next video. And that's, do not, under any circumstances, use trig subs unless you have to. Okay, so on the final exam, you see a problem like this, and you say, oh, that's a trig sub. I'd be happy, but don't do it. Okay, unless I specifically tell you to. Just say, oh, this is the area of a semicircle. If it's a definite integral, say it's an area of a semicircle. If it's not a definite integral, you do have to do what we just did. But if this is like a definite integral or something, just calculate the area using geometry. If you can use a u substitution on these problems, use a u substitution. You can use integration by parts. That's better than trig subs. Trig subs are powerful, but exhausting. So that's our final answer. And again, if this were a definite integral, what's easier? Pi r squared times a half? Or this? That's basically the end of the first video. I want to check my answer, so you don't have to stick around. Feel free to, relax, do some problems, peace out, get it. But if you want to hang out and check the answer together, let's take the derivative and see what we get. What's the derivative of arcsine? I always forget this one. It's 1 over the square root of 1 minus x squared, I believe. Oh, that's a good sign. Sine. Anyway, and we need the product rule. Derivative of the first, leave the second alone. Wait, I'm sure this, yeah, everything's fine. Plus, I get real nervous. I think everything's fine. Plus the first times the derivative of the second. What's the derivative of that second? It's 1 over 2 square root of 1 minus x squared. And then we need the chain rule. So it's going to be a negative 2x on the top. So what's happening here? What is happening here, Jason? What's going on? We have 1 over 2 square root of 1 minus x squared plus square root of 1 minus x squared over 2, and then minus x squared over 2 square root of 1 minus x squared. Well, that doesn't really look like what we're supposed to have. We're supposed to get square root of 1 minus x squared back. So who knows? Maybe it'll all work out. Let's get a common denominator. Get a common denominator. If we make this 1 minus x squared, means we need a 1 minus x squared right here. Oh, maybe this does work out. So now everything has the same denominator. And we get 1 plus, this just becomes 1 minus x squared, right? Square roots cancel. Again, it's technically absolute value, but we know 1 minus x squared is positive here because of our domain. And then minus an x squared. Okay, I'm sure everything's fine. Let's just keep simplifying and see what happens. Wait, I think this is okay. So that's going to be 2 minus 2x squared. We'll factor out a 2. Now you might be panicking right here, but look at what we have. This is 1 minus x squared to the first power. And this is 1 minus x squared to the half power. Subtract the exponents. You get 1 minus x squared to the positive a half power, which is the square root of 1 minus x squared. Wasn't worried for a second. Checks out. Remember, we check our answer by looking at the derivative of our antiderivative, and hopefully the derivative of our antiderivative is our original integrand. And it was. Great. So that's this section. You can do a little warm up now, and then we'll do some more problems. I got more. This is just an introduction. This is just the introduction. You're not expected. I'm not letting you loose right now. We're going to do another one of these and explain things a little bit more. Get some practice. It's okay. Deep breaths. Good luck. Bye-bye.